In this video, we're going to talk a little bit more about equivalence classes. So I want to do a little example first. So we're given the following relation. So we have a relation on Z, and two elements in Z are related if and only if 5 is a factor of 3a plus 2b. And we're asked to determine the equivalence classes of this equivalence relation. As a little exercise, you could try to show that this is indeed an equivalence relation, but we're just going to assume it for this exercise. So let's think about this. So again, we have an equivalence relation, and remember from the previous video, we can just pick an element and see what the equivalence class is of that element. And we can do this until we run out of elements. So let's start with 0. Let's see what's in the equivalence class of 0. Well, this is going to be all integers a such that a is related to 0, or if you like, 5 is a factor of 3a plus 2 times 0. So that's going to be the equivalence class here. And if we think about it, let's simplify this. So this is all a in the integers such that 5 is a factor of, well, 2 times 0 is 0, so it's just 3a. And that's the same thing as saying that I can write 3a as 5 times some integer, maybe let's say c, for some integer c. So this means that 3a has a factor of 5. Well, 3 doesn't have a factor of 5, of course, and 5 is prime, so it must mean that a has a factor of 5. So a can be any number that has a factor of 5. So here it must be, we'll write this here, so this must be that 5 is a factor of a. 3 doesn't have 5 as a factor, so a must have 5 as a factor. So what are the numbers that have a factor of a, or of 5, sorry? Well, 0, 5, 10, 15, 20, 25, 30, etc. And here we have minus 5, minus 10, minus 15, minus 20, etc. So that's the equivalence class for 0. Okay, let's pick a number that's not in the equivalence class for 0. Remember, the equivalence class of 5 is the same as the equivalence class of 0, and we're going to show that in general down here in the next example. But let's do the equivalence class of 1 now. 1 isn't in the set. So this is going to be, of course, all integers a such that a is related to 1, which means the same thing as 5 is a factor of 3a plus 2 times 1, so plus 2. So let's explore what this means a little bit. And the idea for this one will apply for the other equivalence classes as well. Well, a good thing to note, and we can try this, is that the numbers in this equivalence class differ by 5. So there's a chance, because we're talking about dividing by 5 or finding a factor of 5, there is a good chance that that's what's happening. So it's depending on the remainder. When you divide by 5, that's going to be the equivalence class. So let's work it out. So let's try here. Well, when you divide 1 by 5, you get 0, remainder 1. So let's try numbers A. That can be written as 5 times C. So not quite a multiple of 5, but one more than a multiple of 5. Let's see what that looks like. So this is saying here that 3a plus 2 can be written as 5 times some integer. Let's call it integer. We already used c, so let's call this one d. And again, this is for some integer d. And I should say here c as well, so c, d, and the integers. So let's try that a is something where we get a remainder of 1 when we divide by 5. So we get 3 times 5c plus 1 plus 2 equals 5d. Does this work? Okay. And let's just multiply this out. So here we get 15c plus 3 plus 2. Does that equal 5 times an integer? Well, this is 15c plus 5. Does that equal 5d? And, well, let's just factor out that 5. We get 3c plus 1. So that indeed does equal 5 times an integer. Here's our integer. So d is just 3c plus 1. So any number of the form 5c plus 1, so a multiple of 5 plus 1, so if you divide it by 5, you get a remainder of 1, that's in the equivalence class of 1. So here we have that this is things like 1, 6, 11, 16, etc. Here we have negative 4. Negative 4 is negative 5 times 1 plus 1. So that has a remainder of 1. This is going to be negative 9, which is this is 5 times negative 2 plus 1, etc. So it's all numbers that have a remainder of 1 when you divide it by 5. That's in the equivalence class for 1. Okay. So just as a little exercise, use the same ideas that we did for the equivalence class for 1 to show that, I'll just do it up here. Sorry, this is getting a little messy. I'm running out of room a little bit. The equivalence class of 2 is going to be everything with a remainder of 2. So 2, 7, 12, etc. to the right. And negative 3, negative 8, negative 13, whatever, to the left. 3 is going to be 3, 8, 13 to the right, and negative 2, negative 7, negative 12, whatever, to the left. And finally, 4 is going to be 4, 9, 14, etc., going positive, and negative 1, negative 6, negative 11, whatever, going in the negative direction. So there are equivalence classes. And notice, I pointed this out in the last video, these equivalence classes satisfy the definition of a partition, and we're going to explore that in the next video. But every element of the integers is in one of these equivalence classes, and none of these equivalence classes share an element. So each element is in exactly one equivalence class, and there's no equivalence classes that are empty. So this is fantastic. We're going to explore this later. I just want to point that out. And those that are who might have noticed this, they'd said, well, we showed that numbers of the form 5c plus 1 are in the equivalence class of 1. How do I know there's not other ones? How do I know that I got them all by checking here? And the answer is, because we did all cases, all elements fell in different equivalence classes, and this shows the following. If we do have an equivalence relation R on a non-empty set here, then A is related to B if and only if these are in the same equivalence class. So the equivalence class of A equals the equivalence class of B. So we have a little proof here to do. This is an if and only if proof, so we have two directions. So let's go ahead and do this. So let's do the forward direction first. So we are going to assume that A is related to B, and we're going to show that the equivalence classes are the same. And remember, R is an equivalence relation. We have that to work with. R is an equivalence relation, and A, B are elements in the set that the equivalence relation is defined over. So let's assume that A is related to B. And what do we want to show? We want to show that the equivalence class of A equals the equivalence class of B. Remember, these guys here are sets. So we're going to have to show that these two sets are equal. And remember how to show sets are equal? Pick an element in the left set, show it's in the right set so that the left set is a subset of the right set, and vice versa, the right set is a subset of the left set. So that's what we're going to have to do. So let's pick an element in the equivalence class of A. So what does that mean? That means it's related to A. Thus, that means that X is related to A. That's what it means for something to be in the equivalence class. Okay. We need to show this is in the equivalence class of B. And remember, we know that A is related to B. So, we know since A is related to B, and remember that this relation is an equivalence relation, which means that we have transitivity. X is related to A is related to B, so by transitivity, X is related to B. So since A is related to B, and R is transitive, since it is an equivalence relation, we have that X is related, oh, that's the wrong symbol, related to B. X is related to A. That's because we picked it in the equivalence class of A. We know A is related to B by assumption, or here it is, by assumption. And R is an equivalence relation, so it's transitive. So X is related to A is related to B, so therefore X is related to B. And that means that X is in the equivalence class for B, since it's related to B. Awesome. So So we can say that, all right, and it means that the equivalence class of A is a subset of the equivalence class of B. Because we picked an arbitrary element in the equivalence class of A, showed it was in B, so it's a subset. Great. Now, let's do the other direction. So let's let X be an element of the equivalence class of B. Thus, X is related to B. We need to show X is related to A. And we have to be a little bit careful here. Here we have A is related to B. That's our assumption. But remember, R is an equivalence relation. So we can use that to say B is related to A as well, since all equivalence relations are symmetric. So, since A is related to B and R is symmetric, we have that B is related to A. Okay. Now, since X is related to B and B is related to A, and the fact that R is transitive, since it's an equivalent relation, we have that X is related to A, and if X is related to A, that means that X is an element of the equivalence class of A, and thus, I shouldn't write two ands in a row, but whatever. The equivalence class of A is a subset of the equivalence class of B. Putting these two directions together, we have that the equivalence class of A equals the equivalence class of B. All right, that's fantastic. So this says that if two elements are related, then their equivalence classes are equal. They have the same elements in them. Okay, let's do the other direction now. Let me scroll down here. Let's get a little more room. Now we're going to assume that the equivalence class of A equals the equivalence class of B. So they have the same elements. And we want to show that A is indeed related to B. So pause the video now, see if you can work this out. Remember, R is an equivalence relation. Everything in these equivalence classes is related under the relation R, and you know R is reflexive, symmetric, and transitive. So those things should help you out. All right, now that you're back, this direction is actually quite easy. So we want to show A is related to B. So we know that since R is reflexive, A is related to itself, because R is an equivalence relation, so everything is related to itself, and thus, of course, A is an element of the equivalence class of A. But since A and B equal, I should say their equivalence class is equal, since the equivalence class of A equals the equivalence class of B, well, A must be in the equivalence class of B. And what does it mean to be an equivalence class? It means that it's related to B. Thus, A is related to B, because that's what it means to be an equivalence class. Be in an equivalence class. It is related to that element. So we're done. We showed that A is related to B. So that was a nice, simple argument for that direction. And again, this shows concretely why it doesn't matter what representative of an equivalence class you pick. Those equivalence classes are all the same, which is fantastic. Okay, in the next video, we're going to explore the idea of partitions a little bit more and how equivalence classes and partitions are, in some sense, basically the same thing.